Okay, as I told you that the tensor analysis is a generalization of vector analysis. Why I'm saying this is will be clear to you in a minute. So let us consider a vector function f of r. Consider vector function f of r of vector r. Uh, we know that vector function f of r is continuous when, say, at r equals to r naught, it remains continuous when limit of f of r tends to r naught equals to f of r naught, and it remains linear. This f of r of vector function vector r remains linear when f of r plus s is equals to f of r plus f of s. Another property of the linear transformation is that f of lambda r equals to lambda f of r, where lambda is a scalar quantity. Now, a linear vector function f of r is completely defined when f of a1, f of a2 and f of a3 given for any three known coplanar vectors a1, a2, a3. You all are familiar with known coplanar vectors which are not lying in the same plane. Okay, so let's say a vector r equals to x1 a1 plus x2 a2 plus x3 a3. Okay, and for vector f of r, this will become f of x1 a1 f of x2 a2 plus f of x3 a3. I am writing this from the help of the linear property of a vector function. Okay, and the same thing I can also write that x1 is equals to f of a1 plus x2 f of a2 plus x3 f of a3. Okay, so from here consider one more transformation. Let f of ai is equals to bi. Another thing which is r dot ai is equals to xi. So x1 equals to r dot a1, x2 equals to r dot a2 and x3 equals to r dot a3. Now substitute all these things in above quantities, and then f of r becomes x1 equals to r dot a1, f of ai is equals to b1 plus r dot a2 b2 plus r dot a3 b3. Okay, we can also write this like that: a1 b1 plus a2 b2 plus a3 b3, which in finally can be written as phi. If I let this as a phi operator, phi where it is a1 b1 plus a2 b2 plus a3 b3, can also be written as phi dot r. Now this phi, which is a1 b1 plus a2 b2 plus a3 b3, has 9 components in three-dimensional coordinate geometry. Now this thing is neither a vector, neither is not a scalar. Okay, but this is a new mathematical quantity called dyadic. Why I am calling it dyadic? Because it has two components, dia, which comes from 2. Okay, to give you more understanding, let me give more depth example to this. Consider two vectors u and v. U and v are two vectors, and u is a linear function and all three components of V. So U is a linear function of all three components of V. We having a relation like that. U x is equals to kxx vx plus kxy vy plus kxz vz. Uy is equals to kyx is equals to vx plus kyy vy plus kyz is equals to vz. Uz is equals to same zx vx zy vy kzz vz. Okay, so here you can see we have 9 coefficient which characterize the components of one vector into the other. We can also write that U is a, as we say in the beginning of this example, that U is a linear function of all three components of V. So we can also write that, say, maybe we can also write it maybe as like this: U phi V, where phi is a dyadic essential part of this array. Okay, now as this dyadic transforms the vector into another vector space. Okay, so in the dyadic it is ai bi with summation. We know that I it is for. Similarly, a triadic, which is this is a dyadic, and for triadic it is ai bi ci. For tetradic this will become ai bi ci and di, and for pentadic so on and like that. This dyadic, triadic and tetradic is nothing but the tensor of rank 0, tensor of rank 0 rank tensor, 1 rank tensor, 2 rank tensor, and so on. Okay, in this way I am saying that tensor analysis is regarded as one of the possible extension of the vector analysis. Okay, thank you.